Kia ora everybody and welcome back. In this video we're going to start talking about a really important topic called isomorphisms. Earlier in the course we talked about, for example, how groups like U of 10 had basically the same Cayley table as Z4. If you draw out the two Cayley tables, you can come up with a sort of correspondence between the two that make them look like the same thing if you just rename the elements to be different things. So in a way these two groups have exactly the same structure. They have the same number of elements, they have the same number of elements of each order, all these various things. And so the mathematical concept that lets us actually state this more formally and more sort of precisely is that of an isomorphism. So essentially an isomorphism is a transformation that lets you connect two different groups up together in such a way that they're guaranteed to essentially behave exactly as the same group. So here's a definition of a group isomorphism. So let's just go through the definition one step by step and just see what it says. So an isomorphism phi from a group G onto another group G bar, okay, so we've got two groups involved, is a one-to-one function from G onto G bar. Now just a little note before we move on. That onto is an actual very deliberate word. So the function, you read this as saying that the function is both one-to-one and onto. So it's a one-to-one and onto function between G and G bar that preserves the group operation. That means if you take A and B in your group G here and compose them together, then you'll get the same thing no matter whether you take phi of the composition of A and B, so phi of AB gives you exactly the same thing as if you pass A and B through phi first and then compose them in G bar. Okay, so that's the defining property. As well as being a bijection between the two groups, the group operation has to be preserved in this way. Okay, so if there is such a phi, if we can find one, then we say that G and G bar are isomorphic, and we write G with a double squiggle to G bar there. Okay, so I guess we could represent this idea a little bit diagrammatically. So if we imagine G and G bar to be two sets, so this one could be G, this one could be G bar, then what this says is that if I take an A and a B inside G, they have a corresponding phi of A and phi of B inside G bar. So we're using our function phi to take elements from G into G bar like this. So B is going to go to there. Now what the group preservation part of it says is that if I compose A and B together here first to get me a new point which will be AB, and map that through phi. So here I'll have phi of AB. Then I'll get the same thing as if I take phi of A and phi of B and compose them together. Okay, so it doesn't matter whether I compose A and B together first in G and then map them, or whether I map them first to phi of A and phi of B and then compose them, I'll get the same result regardless. Okay, so what we should do is outline a little method for discovering whether or not two groups are isomorphic, and then we'll try it out in some examples. So these are kind of loosely speaking the 4 steps. Now the first one, which is often the most difficult, is actually to define a mapping between the two groups. Okay, so we've got to actually come up with a phi first that takes G onto G bar that has that may or may not have the properties we want. Okay, so this is the part of the question where we have to be a little bit inventive. We have to actually come up with some kind of mapping to test that we can then work on. So this part is the hardest bit because it involves us having to be a bit creative rather than just test something using a procedure. Okay, so once we have ourselves a phi, we then need to show that our mapping phi is one-to-one. So what that means, that says we need to show that if phi of A is equal to phi of B, then the only way this is possible is if A equals B. Okay, so we're showing there's no way that we can have two different elements in G mapping to the same element in G bar. Okay, once we've done that, we can then show that phi is onto. That means that for all G bar in our target set, show that there exists a G in G such that phi of G equals G bar. So what I've said in sort of in symbol notation here is that for everything in our target set G bar over here, we can find an element in G that maps to it. That's all that says. Okay, so once we've done steps 2 and step 3, we've then showed that our mapping phi is 1-to-1 and onto, i.e. that it's a bijection. But the last thing that makes it an isomorphism is to show that it's operation preserving. And that means to show that phi of AB is equal to phi of A, phi of B. Okay, so let's try these ideas out on an example and see how this works. So here's our first example. We're going to show that the real numbers are under addition are isomorphic to the positive real numbers under multiplication. So maybe if we think for a second, under what kind of function takes addition to multiplication and vice versa? So we need to come up with a mapping that takes real numbers onto positive real numbers, where addition is turned into multiplication. Okay, and so maybe if you think about this for a second, that you might even want to pause the video and do so, then one possibility is to look at an exponential map, right? So I'm going to choose for step 1, phi of x to be 2 to the power of x. Because I know that if I add x and y, that corresponds to multiplying 2 to the x and 2 to the y. So maybe this is a good choice to show these two groups are isomorphic. Okay, so we've done step 1. We've defined ourselves a candidate mapping that we think might work. Could have used e to the x, doesn't really matter. Any exponential is going to do the trick just fine, apart from 1, I suppose. So let's just follow the procedure and just see how all these different steps work. Okay, so now we got to show that we have one-to-oneness. I'll just put that in quotes to remind us what we're doing. So that means we're going to show that if phi of A is equal to phi of B, so assume that phi of A is equal to phi of B, then we know, taking a logarithm, this implies that just take log to the base 2 of 2 to the A equals log to the base 2 of 2 to the B, i.e. A equals B. Okay, so we're just assuming that we're allowed to use some of these things from calculus that we've met before. So the most important thing to focus here on is on the structure of what we just did. We assumed that phi of A was equal to phi of B. We used this to show, therefore, A equals B, and hence our mapping is 1-to-1. Now we need to show that our map is onto. So again, we've got to show, that means we have to show that for every element G bar in G bar, there's a mistake on there, sorry, it should be G bar, we want to show that there is a corresponding G in G such that phi of G is equal to G bar. It's a lot of G's in one sentence. So in our example, we have to show that for every G bar and G bar, so that means for every positive real, so let y be a positive real number, we want to find x in the regular real numbers such that phi of x is equal to y. So 2 to the x is equal to y. Now, we can see that x equals log to the base 2 of y is such an x. Remember that y is a positive real number, so we're not going to have any negative numbers, so we'll be able to take logarithms of it no matter what, and x will therefore be whatever it will be. It can be anything from negative to positive, that's fine. So for every positive real number y, log 2 of y is defined, and it gives us the x that we need. Right, so at this point in time, we've now shown that our mapping is 1-to-1 and onto. The last step in showing that they're isomorphic is to show that that our map phi is operation preserving. So I'm going to take 2, in fact, let's just define some elements. So let A, B be in our first group, then 2 to the AB equals 2 to the A plus B. Let's get that correct. 2 to the A plus B. So this is where I take phi of A plus B. Let's just make a little notation about that. Is equal to phi of A times phi of B. Because the group operation in our group G, which for us is the real numbers under addition, is addition. And then the group operation in group G bar, which in this example is the positive reals, is multiplication. And just by standard properties of the exponential, that is true. Therefore, we conclude that the real numbers under addition are isomorphic to the positive real numbers under multiplication, i.e. they're the same group as far as the group theory structures are concerned. So let's do another example, and this one's a really important one, and we've kind of alluded to this one a number of times already before we've actually got to it. So this one is about cyclic groups, and it says that an infinite cyclic group generated by A is isomorphic to the integers under this particular mapping, which takes the exponent onto just the integer itself. And then it specializes to if we have a finite cyclic group, i.e. a cyclic group of order n, then the cyclic group is isomorphic to Zn under, again, the mapping that takes the exponents into the set mod n. Okay, so we'll go through and prove this. We'll follow our procedure. Quite nice that we've been given the phi already, so we don't need to worry about that part. So let's start by just following the steps. We come on in at step 2, and this is the one-to-oneness test. Right, so essentially we have this one already. This is theorem 4.1, which says that a to the I equals a to the j. So that's our phi of a equals phi of b, if and only if I equals j. That's the infinite case, and in the finite case we had I equals j mod n. Okay, so I've already done this one as a theorem, so we don't need to reprove that now. Okay, number 3 is onto. And again, the way this problem has been set up, it's kind of onto, we say it's onto by construction. Okay, because we can get to any integer k, because the way the element of our cyclic group has been defined lets us choose any integer k we like to go in its exponent here or here. So onto-ness there's not really anything to do here, so we'll just say that one is by construction. You can't come up with an integer k for which there is no element a to the k, because a to the k includes the k in its definition. Okay, so the piece we actually have to check is that our operation is operation preserving. So let's do the infinite case first. This one says that phi of, so I'm going to say let a to the I, a to the j be members of our cyclic group. Then phi of a to the I, a to the j is equal to phi of a to the I plus j equals I plus j. And in the order n case, same kind of thing applies. Again, I'll just have the same kind of I and j. Phi of a to the I, a to the j is equal to phi of a to the I plus j, which equals I plus j mod n. And these are just the group operation in the integers here and in Zn here, respectively. Okay, so that means that our cyclic group, no matter what it is, pretty much behaves the same way as the integers. And what we'll develop in the subsequent video to this one is an example of large lists of properties that are shared between two groups that are isomorphic. And in fact, pretty much any group theoretic property is the same between the two. So what this theorem is, What this example is basically telling us is that Zn and Z behave exactly the same as any other cyclic group, which justifies us pretty much focusing our attention on these when we're solving problems involving cyclic groups. Okay, let's do an example where it breaks down. Here we're going to map the integers under addition onto the integers under addition. So we're looking at a potential isomorphism from a group into itself. These have special names that we'll go into soon, called an automorphism. Anyway, our mapping is given by x is mapped onto x cubed. That's what the arrow with the little bar means. So we're going to show that this is not an isomorphism. Okay, so the groups are obviously isomorphic to themselves because they are the same group. But this particular mapping is not an isomorphism. Why is that? Well, let's just jump straight to the operation preserving part. If I look at phi of x plus y, that equals x plus y cubed, which equals x cubed plus 3x squared y plus 3xy squared plus y cubed, which is not, in general, equal to x cubed plus y cubed. So phi is not an isomorphism. Now, note what we don't conclude here. It would be tempting to then say, therefore, these two groups are not isomorphic. That's not true. Okay, we've just established that the mapping we found is not an isomorphism. We can't therefore conclude that the groups are not isomorphic. In fact, they are because they are the same group. But all we have shown is that the mapping we came up with is not actually an isomorphism. Right, now I just want to take attention away from the math video for a moment. As I speak, my university, Massey University in New Zealand, has just observed 1 minute silence for the victims of the terrible terrorist shooting in Christchurch on Friday, March 15th. So I thought it would be appropriate to observe a minute's silence within this video as well. If you're watching this at a future date, feel free to skip forward that minute, but I'd like to pay my respects by doing this. Thank you for your understanding, and we'll return to the math now. Alright, so for our next example, we're going to look at just an example of a couple of cyclic groups. So we know now, because U of 10 and U of 5 are both cyclic, they must be isomorphic to Z4. And we can see that because U of 10 is a cyclic group because, for example, if 3 is a generator, because if I take 3, and then 3 squared is 9, and then 3 nines are 27, which is 7, mod 10, and 7 threes are 21, which is 1, mod 10. So 3 is a generator, and therefore U of 10 is isomorphic to Z4 under the isomorphism 3 to the k is mapped onto k, mod 4. Okay, because the order is 4, so for example 3 to the 5 will be mapped onto 1. Alright, so that's cool. U of 5 also cyclic, because if I take, for example, 2 as a generator, 2 2s are 4, 4 2s are 8, which is 3 mod 5, 3 2s are 6, which is 2 mod 5, 6 2s are, 2 5s are 10, which is a big confused mess. Let me just back up a second. 2 3s are 6, which of course is 1 mod 5, not 2. That's why it didn't work. Okay, so therefore we've got a generator, so again I can say that 2 to the k gets mapped to k mod 4 again. Okay, so that's cool. So we can establish by our cyclic groups example, we establish that these two U groups are both cyclic because we can find the generator. Now let's just look at an example of a U group that's not isomorphic to its corresponding Z group of the same order. So here we've got U of 10 and U of 12. They're both U groups with 4 elements. They're both of order 4. And I've also put down the Cayley tables for both groups. Now I want to show that these aren't isomorphic. So kind of the most immediate feature that perhaps jumps out is that in U of 12, everything squared is equal to the identity, whereas in U of 10, it's not. So this is a real strong clue that I can't rearrange U of 10's Cayley table and renumber the elements so that I get U of 12, because they look like they're fundamentally different things. So let's just see how we might better do that mathematically. So we can say in U of 12, x squared is equal to 1 for all x. Okay, all of our elements square to 1. They each have their own inverse. So what we're going to do is we're going to let phi be an isomorphism. And we're going to take it from U of 10 to U of 12. Okay, and we're going to take advantage of this everything squared equals 1 idea to show that this is not going to work. So in particular, I'm going to show that phi of 9, okay, 9 is equal to 3 squared. You notice in this group here, 9 is equal to 3 squared. So this is where I'm going to make it break. So that's equal to phi of 3 times, I'll just do it in 2 steps, 3 squared. Happy with that? Which is equal to phi of 3, must be equal to phi of 3 if phi is an isomorphism, which is got to be equal to 1 because everything squared is 1 in U of 12. But we're going to also show, we've got another square here, which is 1. 1 squared is 1. Phi of 1 also has to map to 1 because it's phi of 1 times 1, which is phi of 1 times phi of 1, which also must equal 1. So no matter what isomorphism we have, phi is not 1 to 1. And not an isomorphism. And because phi was just set up to be a general isomorphism of any sort, there cannot be any of them, and therefore these two groups are not isomorphic. Okay, showing not isomorphic usually involves showing that some property of the groups is different. Here we've got the fact that all things square to 1 in one and they don't in the other, and so we've taken a square that's not 1. We could have used 7 as well, and shown that they all have to map to 1, which makes it not 1 to 1. Okay, we'll do one more example, and then I think we'll call this video quits. So here's my final one. In this example, we're looking at 2x2 matrices. We've got some fixed matrix M in our group of 2x2 invertible real matrices. And the mapping, I want to show that G is isomorphic to itself through the mapping phi M, where phi M is defined to be M times A times N inverse, a conjugation by M of any element A. Okay, so it's useful to know that this is an isomorphism. So let's see how we go. So first off, we better actually check that no matter what our matrix is, that phi M is going to actually be still in SL2R. So first is, let's change color, is phi M of A in SL2R. So this is, we have to sort of establish this. This is checking that our operation is actually well defined and keeps us in the set that we want. So we'd better just check this first. So the determinant of phi M of A is equal to the determinant of M A M inverse, which by the properties of determinants is equal to the determinant of M times the determinant of A times the determinant of M inverse. Right, so determinant of M, so A equals is just whatever it is. Determinant of A is in a special linear group, so it's got determinant 1. And then it's times 1 over the determinant of M for the determinant of inverse equals 1. So first off, our matrix does indeed give us a matrix in SL2R. Okay, they're 2 by 2 invertible matrices with determinant 1. I may not have mentioned that before. Okay, so we have that our matrix is well defined, and our mapping does indeed take us where it claims to, so that's good. So we can move on to the next part. So step 1 is to define the mapping, that's done. Step 2 is to check one-to-oneness. Alright, so assume again that phi m of A equals phi m of B. Okay, i.e. M inverse is equal to M inverse. Now quite clearly, by cancellation, this implies A equals B. I'm just going to right multiply by M and left multiply by M inverse. So phi M is 1, 2, 1. Now we need to check onto-ness. So now we need to choose an arbitrary element of G, and we seek an A such that M inverse, that's phi of A, is equal to B. Okay, and this is equivalent to A equaling M inverse BM, and also that's what we want, right? This is the A that we're after. Note that det A equals 1, so A is an element of SL2R, and our mapping is onto. Okay, just using the same determinant logic as I used before. And finally, we've got to show that phi is operation preserving, which I'll often abbreviate to just OP. So phi m of AB is equal to M AB M inverse, and I can just insert an M inverse M in the middle here. It's just the identity, and that in turn is just equal to phi m of A times phi m of B. So my operation phi here is indeed an isomorphism. So hence phi m is an isomorphism. Okay, so we're going to see what we can do with these things in the next video, but for now we've kind of got the general idea. We know what it means for two groups to be isomorphic, and we also know what's involved in checking that a given mapping is an isomorphism. And that's a good starting block for our next video. So until then, we'll see you later.